Hey guys, welcome back to IBM Systems Back to School 2020. We're heading towards our session number 5 of 8. And today the topic is infrastructure for artificial intelligence. So we have on board Mr. Andrew G back on stage after 1 week off. And the idea is to discuss the importance of having an infrastructure, or as per se, as some articles like to say, an information architecture agenda for your artificial intelligence applications project. Okay, so moving on the slides.
I'll fix the title in that first one.
Well,
I've got the II wrong. Okay.
Yeah, well.
Okay.
Little bit used to that. So this is all about a series of 8 events that we are running here in New Zealand. As you may know, we are not having the IBM Technical Universities globally speaking and face-to-face events that we have. So we decided to do a version of it, a small version of it, containing 8 sessions, Asia Pacific sort of time zone. So we are going to have a session about 40 to 50 minutes, and after that we will have some questions and answers, and hopefully we can answer all of them. Okay. So as I said, we're running now the session number 5. We still have 3 sessions to go. On the portal, on the event portal, you may find the replays, the material for downloads, and also the registration links for the remaining sessions. Okay, I reckon that's pretty much it for introduction. So yeah, Andrew G,
thank you. I got the title right on this one. So
yep.
your AI needs an IA, an infrastructure architecture or infrastructure agenda. So it's what we're talking about, the structure of the whole environment. But first, we've got a couple of rather what I think are very important statements to make on an AI from IBM. And as you'll be aware, we have a new CEO in Arvind Krishna, and he wrote to Congress because of the challenges, in particular in America, that they're facing right now. That IBM will no longer offer general purpose facial recognition or analysis software. The company will no longer develop or research such technology. And his statement here is IBM firmly opposes and will not condone use of any facial recognition technology, including human facial recognition technology offered by other vendors for mass surveillance, profiling, or violations of basic human rights, etc. So we have some customers, obviously, which are using our existing technology, and they will continue to have support, but there will be no more offerings and no future development for general purpose facial recognition technology. And part of this was brought around by one of the topics we'll touch on shortly. In 2018, the 2 researchers here went through lots of commercial facial recognition systems, including IBM's, and they discovered they were biased. And that is because when training models are made, it requires a subject matter expert or an extrapolation to occur. And so what you end up getting are inherent biases in your data models and the data models, or sets as they call them, tool sets. And so they found that just about everybody's had biases in there. In fact, one of them, I think famously, out of several thousands of mugshots, incorrectly identified 28 US senators as being those people in that. So yeah, biases are not good, and we're not doing it. And the second thing is, on July 23rd, there is an IBM Data and AI Forum, particularly ANZ focused. So for our listeners that are in our area or other areas that might want to learn more about data and AI. And in fact, we've got a data and AI sort of division now within IBM. So a lot of the cloud packs for data and things like that will be in the under the remit of that team. So IBM developed a thing called the AI ladder. and it's to try and help businesses understand where they are, just as we had a journey to the cloud, and we have, you know, the 4 stages going through from adoption through to full deployment, etc. Of the cloud. We've got the similar structure for the AI ladder, and it's written by a gentleman called Rob Thomas and published by O'Reilly Press. And the reason I put the preamble on is that Rob Thomas is actually speaking at that AI conference, the virtual conference we're having in July. So we say there's 4 steps, 4 rungs on the ladder, which is talking about collection of your data, organizing the data, analyzing it and infusing it, or you may hear the word inference or infer, which we use for some of our servers. So collection of the data obviously is where's it coming from, and how much do we have. Organizing it is the worst step. I would be quite frank. I would say 80% of your time will be spent in organizing, categorizing, governing that data, then doing the analysis, which is relatively straightforward, and then using that, the models that gets created by the analysis system, and going on and inferring or infusing it into your business. So one of the first things we've got to define is how much and how diversified and how good is the data. You know, the old garbage in, garbage out still stands. So most data analytics projects will fail due to a lack of preparation, a lack of data, the sheer quantity, and bad data. And it's not easy. A lot of data cleansing may be required. So if you have, you know, we always say, oh, the CIO read a magazine on the flight on the way back and we think this is the latest thing. The investment that a client will make, 80% of their time will probably be spent on cleansing the data. So an infrastructure architecture is the foundation of the structure for an organization. So it needs to be open and flexible. So if you've only got an OLTP or a system of record, you don't have enough diversity, you don't know what social empathy is going on, you don't have weather information, what's actually happening right now to provide data. So you may have to collect it or purchase it from many other locations, get it from a hybrid multi-cloud for an Internet of Things, etc. So, and that leads us down into where do we store all this data? You know, if we can get all this from all these different places, and obviously the most flexible environment is going to be a hybrid multi-cloud when you have all those data sources available, bring them down to a storage location. So a system of record is typically structured data. It's a database. So we know what we've done transactionally, but we don't know, we have no relevance to any of those things other than if we had a sale on that weekend or something. Most of the data you're going to be working with is unstructured object data. So where is this going to be stored and managed? As I said, 80% of your time will be spent cleansing it, categorizing it, organizing it, and governing it. And governing comes down to, if you make a decision, so if you decide to use loan applications or credit applications or particularly anything financial, if you're making a decision based on some data that a client gives you, you better be very sure that you can back up how that decision to approve or deny has been founded. And that's part of the governance that we talk about. It's not just about making sure that the right people and only the right people have access to the data. It's also about them being able to change that data, right? So people could falsify sales figures. We've had many companies and several banks that's cost them millions in fines where people have forged sales numbers. So yes, they were entitled to use it, but the data itself wasn't governed. So, and as we came back to with the visual recognition, does it have bias? So I'll hand back over to Ablio, and we'll talk a bit about some of the customer demands and the storage.
So, so it is one way we say about architecture. Yeah, we're talking about the whole end-to-end devices, right? So, and on this presentation here, we're talking about the fewer algorithms and also some infrastructure that we have in place to accommodate that. So we have some requirements in order to deliver an efficient artificial intelligence application, right? So it doesn't really matter if you have a beautiful algorithm that runs and do everything that you need. If you don't have the right speed, if you don't have the right amount of capacity to accommodate all these data that you are needing to handle, your project will be not as efficient as it could be, right? So we have some requirements. So lots of data. So what do I need for my jobs, and where is it placed, right? How can I automate analytics on new ingest data? How do I ensure my limited high performance storage does not run out of space? If you have just a few amount of just a few space on flash storage, and you need to run a huge big data application, you will be running out of space. So you need more data, more capacity on your storage. So how do I ensure data fidelity? What is the latest version? So you need to have a system that can orchestrate and manage that for you, right? So how can I easily, efficiently provision, test, deploy, and scale the next generation of workloads? What I mean by that is that during the phase of our AI ladder, you will see that there are different storage requirements. So you need to have a system or an architecture that accommodates that, right? Well, easy data science and storage means workloads. So our data science can find and prefetch the data that he needs for his machine learning jobs without any knowledge about spectrum scale. So that's the topic. So if we can move to the next one. Yep. So basically, when you run your AI applications, you will see that some of the data is required all the time, and some of the data is not required all the time. So first, you need to have an AI on your file system that says that which data is hot, which data is not hot. What I mean by that is that it would be beautiful if we could have budget for everything is running under a flash system tier. But unfortunately, this is not cost effective for all of us. So what we can do is that we identify and we dive on this data lake or data ocean, and we verify which data is hot, which data is cold. We will keep the hot data into most expensive tier that you have in hand, and we will keep the cold data in a less expensive tier. Basically, that no rocket science. So moving on. Yeah. So the thing is that this also needs to be dynamic, right? Because if you are running a project and an AI training model, you are training your model this week or this month. Maybe next month you will be training another model, another application that you need to run, and they have different storage requirements. The point is that you need to have flexibility while your AI analytics require high performance, low latency storage to keep the expensive CPU, GPU busy, right? So this is all about balance. Moving on. Okay, so you can do like click, so we can show we can see the whole picture. Yep, that's the bit. So we have basically ingest, organize, analyze, machine learning, and deep learning. So basically on the ingest part, on the ingest phase, we have transient storage requirements, which is throughput oriented, software defined, temporary lengthy. So this doesn't need to this doesn't need to be there forever. So we have a global ingest, throughput oriented, globally accessible, is a capacity tier, Nila SAS, cloud tiering S3, whatever. So chip storage, right? And then you have the fast ingest real-time analytics type of tier, which is basically performance tier. We have flash system, we have SSDs, this kind of system. And so you have the same type of organization of the data and requirements of the data through the whole pipeline, okay? What I mean by that is that this needs to be ran by a single entity, a single file system. Otherwise, it will become complicated to manage. So that's why the importance of having a mature file system, just like our Spectrum scale, right? Yep, I reckon that we can go further. In the next slide, please, Mr. G. Yeah, one more. Awesome. So to put names, so we have basically Spectrum Scale, IBM Cloud Object Storage, Spectrum Archive, and Spectrum Discover. So we will be talking about this no spoil alert in 2 weeks' time in one of my sessions about Scale, Object, and Discover. But just to let you know that this is what we are talking about. So basically, performance tier and capacity tier, and it needs to be seen like a single namespace. So all applications needs to see one single system, right? So I reckon that my last slide, which is the next one, it will have, you guys will have a clear view on what I am talking about. So basically you have the global namespace tier, what we call it IBM Spectrum Scale. Underneath you will have any kind of storage that you may have in on-site, on-prem or not. You can have flash, you can have disk, you can have tape. You can click on next because it is a very fancy type of slide where I put it lots of animations. So I put all my knowledge on PowerPoint on this one. So yeah, we need to use it. But basically, underneath the Spectrum Scale tier, you will have all the tiers available. Above it, you will have the protocols that we support and the application that we are currently running in most of our clients that runs AI application mature environments, right? And very cool stuff, which is in the right side of the slide. It is right, so it's left. So this one here that calls IBM Cloud, AWS, and there are some two machines here. Basically, what I mean by that is that, okay, if you want to have your file system running, but you don't need to have an on-prem infrastructure, you can have it as a service running on the cloud. So you can have actually Spectrum Scale. You can buy from AWS Marketplace. You can buy from IBM Cloud Bluemix. And so it is very flexible from this point of view, right? So, and as I said, just to highlight the tiers, that this is the topic from AI point of view, we can have flash, disk, tape, we can have JBoss, we can have IBM Cloud Object Storage on-prem, off-prem in the cloud, or hybrid. We can have Azure, AWS, Swift. So all this type of data can be seated behind the global namespace. All that to give you flexibility, to give you speed when you need it, give you capacity when you need it. I reckon that's pretty much it from the storage point of view. Thank you, Mr. G.
Thank you, Ablio. In fact, I said to Ablio, just put some storage stuff in for me, because obviously my section's the boring power bit that comes up next. But this is really good because it's shown in particular the amount of applications that are now using data and are running in clouds, be they in an aggregator or even an on-prem hybrid situation, and how containers are being utilized for these services. So this item here up in the top left-hand corner is really good with TensorFlow and Spark, etc., Kafka. And of course, IBM has a solution in this area, which is called the IBM Cloud Pak for Data. And obviously, with our purchase of Red Hat, etc., there's been a big shuffling of which middleware will be used to do what. And a lot of the circumstances have changed over the years. We've really been embracing the Red Hat, and we've decided to build all our cloud packs on top of Red Hat OpenShift. So back to Abilio's previous chart with all those containers. So this is a rough breakdown. There are several hours of discussion on this. I'm not an expert. Please don't expect a deep dive. But so built on top of OpenShift. Now you see here there's some little notes like, say, Power Q4. This was a pre-announced chart. It was slightly delayed coming out on Power while they were doing the Red Hat testing and verification. And so this came out Q4 last year. the Cloud Pak for Data. So here we have the OpenShift base and the core platform, which is a recommended install, which gives you some projects, some scripting, etc., some added services management, and these are required. This little green box down the bottom here, and it includes services from Watson Studio and Watson Machine Learning. So this is part of the pack. Then there are additional analytics and environments. Now, remember me saying right back at the beginning that governance is really important. So we've actually got predefined models, including governance and including security, that are built into this pack. Then we have the data warehouse coming in. I think that's SMP is for using the solutions that have got multiple GPUs in them. So for example, our IC922, which will come along later, so we'll be able to take advantage of that pack which came out. And massively parallel is something else coming first, supposed to be first half this year. And then of course, obviously we've got premium add-ons that you can come on with more machine learning accelerator and Watson Studio Premium. So when you buy the Cloud Pak, you buy an entitlement and you can use the various bundles and products that are inside the pack up to your entitled purchase, shall we say. So just want to touch that quickly because we've got one and it was building on top of the container system that Ablio has just covered. So quickly going through the power roadmap, which will stay here. If you paid attention for the last two sessions, you'll see we're at Power 9 and we've got some traditional in the commercial world. We really talk about SMT8 and then we talk about on-chip accelerators. So SMT8 isn't so relevant anymore. AI and machine workloads tend to use more cores than threads. And but the OpenCAPI and the business warehouse enhancements, as it were, are far more important. So looking quickly at the Power 9 processor design, it's very symmetrical, and you see basically 12 building blocks here. But if you notice, the building blocks are also symmetrical, and they are in fact 24 building blocks. And it looks a bit like this. Now, if we break that down, so here you can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and we break that down again, starting at the right-hand side, we have the two units in a 64-bit slice, and we put two of those together and we form a thing called a super slice. And two super slices together, so it's like 1, 2, 4, it's binary, we now have an SMT4 core. So these are what we use in AI, ML, and DL, because if you look back at the chart, so this is half of one of those. So each of those little works as core effectively. So we've got 24 of those on a chip, whereas the most we would do for a commercial workload would be 8. So this is what we're doing. So here's our range. We have our mission critical workloads, commercial systems on the left-hand side, and we have the big data workloads on the right-hand side, and that's what we're going to be talking predominantly about today. We've got 3 stages that we talk about typically, which is data, training, and inference. And so the LC922 on the left there is basically our data server, and it probably does some of the best workloads for Spark workloads. It's probably one of the best servers. I'll include a chart on the capability of that when we do the LC922 bit. I've realized it's not in this presentation. Then of course we have the AC922, which was our first machine that we released. This is the one with GPUs on board, and we'll cover that. And our latest addition to the team is the IC, which is an inference server. And what you will see, you can see the number of drives on the front. We've gone from 12 on the LC to 24 on the IC. You will see the IC will replace the LC in time. So Europe has removed it already, the LC. The rest of the world's going through its natural lifespan. But we think the IC will take over the role of the LC. So some of the advantages we have on power systems versus x86. We've talked before about the bandwidth to the processor. We've got around about 1 terabyte per second bandwidth to the processor, and we have around about 7 terabytes per second in the processor. The Power 9 systems have got PCIe Gen 4. So it depends when you start seeing the PCIe Gen 4 adapters to take full advantage of it. Most of them are still Gen 3, but we're there and we're ready. So when PCI 4 cards come out, then we can take them. There's no need to replace your system and your server just to do it. So we have 64 gigs a second, a bidirectional transport up from 32 gigs, and we have 192 gig aggregate between them. So the LC922's got 7 PCI slots, AC's got 4, because it's more of a specific GPU box, and with 3 using CAPI, which we'll cover later. And the IC's got 10, and 4 of those are for CAPI. So CAPI, CAPI2, and OpenCAPI 3, we will cover briefly. They are interfaces for accelerators that we have built into the power processor. And similar with NVLink, we have NVLink 2, which is GPU to CPU at 300 gigs a second, and GPU to GPU that's at 300 gigs a second also. And that's with an AC922 with 4 GPU. We can put more into those machines. Now, if you compare that to the 32 gigs a second for PCI Gen 3, talking from the GPU to the CPU. So CAPI originally allowed GPU to GPU conversations, but we were the first with CAPI that had GPU to CPU. So IBM's got that extra bandwidth of bringing things into the processor. The Tesla, 16 or 32 gig with 900 gigs a second, it's 1.5 times the Pascal P100 GPU. And we have a coherent connection to the CPU and memory in the AC922, so we can address memory directly rather than having to go down through the PCI bus, through the processor and out to memory. We can do direct attachments, so much improved bandwidth and performance. We talked briefly last time about memory bandwidth. In our scale-out servers, we do 170 gigs a socket versus Intel's 128, so 1.3 times the bandwidth of x86 systems. And just a reminder, the best memory bandwidth is with typically 8 of your 16 slots, because the first 8 will run at 2666, and then they will slow down once you go past the 8 and you fill the next quad. So some machines allow you to put half the memory slots in, which would be like an LC922, give you 512 gig. We don't need those massive memory stores like we do for SAP HANA with multi-terabytes of storage in these machines. These are a scale out. So smaller memory, lots of cores are important here. And on the IC922, we can do 1 terabyte with half the slots filled. AC922, you don't have any choice. All the slots must be filled. So you get the performance you get. And you can see the numbers we've got there. So we get 2 terabytes in the 922 and the IC922, and the LC is limited to 1 terabyte. So we're just going to cover the LC922. I'm just keeping an eye on my time here, because there's a lot of feeds and speeds. So we have 16 or 20 or 22 cores of 4 threads per core running at various clock speeds in the LC922. Therefore, because the 922 means it's 2 sockets and 2U tall, we can have 1 socket or we can have 2 sockets populated in this box. So we can have 16 through to 44 cores available in the system, whereas in a commercial box, the maximum you would see would be 20 or 22, 24, depending which platform you looked at. So we don't need SMT8, therefore we get more cores for these workloads. A thing to watch with the LC922 is if you buy a 1-socket board, you cannot, unlike a commercial system, you cannot add that second processor. So you've got to think about that when you're starting, or you cluster, right, which is what Linux cluster stands for, LC. In the storage, we have 12 large form factor, or SFFs, they just have a different carrier. It has an integrated SAS controller, no cache or 4K disk support, so it only uses 5K disks, 112, sorry. Add a SAS controller if you want 4K disk support. 4K disks tend to be a little bit cheaper these days. You may put some NVMe drives in there as well, but it requires a separate HBA. There are multiple, and there are at least 8 with 1 option and 3 or 4 others, so 12 potential storage configurations when you're working with the LC922, and it's far simpler with an IC922, which might be one of the reasons the LC is looking towards retirement in Europe. We can add another couple of small drives in the back for the OS, but it reduces your I/O slots. So it was our machine for doing Spark workloads, high data workloads when it initially came out. On this machine we have a single processor cross-bus connect at 60 gigs a second. But if you don't think that sounds very high, go and check out Intel's UPI. They use a different metric, but you can compare it and convert it, and I think you'll find it's far slower than 60 gigs a second. So again, it's one of those, we can do more with less. So we have fewer cores, but we actually have better performance per core anyway. Have a quick look at the IC922. This is as used in Summit and Sierra, which are, when I last looked, still #1 and #2 in the supercomputers of the world. And in fact, Summit got an upgrade. They added some more nodes into the cluster. I think just under another 2,000 petaflops or something, just below that, added late last year. As technologies leapfrog each other, you'll see that this will be overtaken in time by something else. But it's a very powerful statement from IBM's technology to be used in #1 and #2. So a couple of different models of the IC922, and remember, these are the ones with the GPUs in it, and we'll have a couple of images coming up on this. We have the GTH, and your letters may change by geography, but two models essentially, a 32 or a 40 core, 4 threads per core, and that can have 0, 2, or 4 Tesla V100 GPUs, and they're air-cooled. The IC922 GTX has more cores, so 36 and 44, and slightly faster, and it must have 4 GPUs minimum. It can have 6, but it's water-cooled, and you'll see a picture of that shortly. And the storage is rather minimal. There's only 2 slots, but we can have 4 terabytes of SATA hard drives or 7.6 terabytes of SSDs in them. So these are crunching things. These are doing a lot of graphics work. And the processor internet on here is a 4-channel interconnect on this one. So here we go, a couple of pictures. The big orange or copper blocks here are the GPUs, and the processors are these bronzy colored ones just to the side here. So we see this has got fully populated, air-cooled 4 GPUs in the system and 2 sockets occupied. And over here you can see the first one's partially hidden by the angle of the shot, but there's 3 across this row here at the front, and then another 3 on this side here, and the CPUs and memory all water-cooled with the 2 feeds coming out to the side here. So I mentioned NVLink too, and what's better about this. So you notice that those GPUs were actually on the motherboard. So there's still technically a PCI connection, but they're not a PCI board. So we use another technology we're able to take advantage of here with NVLink. So the first traditional GPU connectivity goes into a PCI 3 bus. And here you have the connection on the left-hand side, talking at 32 gigs a second to the processor, and the memory bandwidth on one of those systems is typically around about 76 or so gigabytes a second. When NVLink 2 came out on a traditional system like an x86 system, it allowed GPU to GPU connectivity at around about 50 gigs a second. Use what we call a brick in there, but we're still talking at 32 gigs a second to the processor. On the Power 9 processors, we changed things. So what we've got here is we've got 3 bricks effectively per GPU. So each processor has 6 bricks, and each GPU has 6 bricks. So 3 connections go between the processor and the GPU. 3 connections go between the GPU to the GPU, and so on. So there's 6 here and 6 here. And that's 150 gig interconnect between the GPUs compared to 50 on your x86, and 150 CPU to GPU compared to 32. So this is the advantage that we have with the Tesla onboard GPUs. They have far faster throughput, far more throughput. And here's a wee diagram, should I say, of, because I said we could do 6 obviously the things change. So here on the left-hand side, we can see that we've got each of those lines coming into the processor is 50 gig and bidirectional, 25 gig nominally. So 3 of those combined together, you've got the 150, another 150 here. So we've got 300 gigs of bandwidth from 2 GPUs, and same on the other processor. When we go to 6 GPUs, we've still only got 6 connections. So here we have a different connection again. We're still, each of those is 50. So you see we have 100 gig here, 100 gig here, and 100 gig here. So we've got 300 gigs still, but the GPU to CPU is only 100 rather than 150. But we can do more. So it depends where you're going to get the benefit. If you're going to get the benefit from more GPUs, put the 6 in, they'll go slightly slower to the CPU. But if you you don't need that, then absolutely you're going to get better throughput on the 4. CAPI, cohesive connections to memory, as the processor does. So when you traditionally drop a processor, an accelerator or some sort, being a FPGA or a GPU in, it comes down the PCI bus at 32 gigs, talks to the device driver, talks to the processor, and talks to the memory. We use CAPI, which has an interface built into the processor. When you looked at that processor diagram, there were the 12 blocks, but there was a big block down the middle, and the accelerators are actually built into the chip there. So what we have is the accelerator can access the shared memory directly. It doesn't have to go through that system, so we can do things far more quickly, and it's twice as fast as uses PCI. Actually, uses PCI Gen 4 now. I've got Gen 3 there. OpenCAPI, so part of the Open Power Foundation, we have OpenCAPI. They use a different connection. They use a thing that came out of the 25G workgroup. And in this case, the adapter only draws power from the PCIe slot, and the adapter connects to an OpenCAPI interface at the processor. So here we go. We've got a PCI slot with, in this case, an FPGA. And we see we're only pulling the power from the PCI slot, but the data connection is going down a 25G link. Now, 25G link is 50 gigs per second bidirectional. Haven't I just mentioned that somewhere before? Here we go. So the bricks are shared between NVLink and OpenCAPI. So you'll see here that only 2 of the bricks can be used by OpenCAPI, or 3 bricks can be used by NVLink. So you can, they are mutually exclusive to some extent. So depending on what you're doing, if you're bringing CAPI cards in, or you've got NVLink, if you've got GPUs, or some cards such as InfiniBand adapters take advantage of the CAPI interface. So you have to think about what you've got, but the interface is far faster. So we're using 50 gigs a second now for a card that drops into a PCIe slot. This basically just covers, again, what I've just walked you through. So I'm not going to go through it. It's just there for your reference. And the IC922. So this is a storage-rich inference server. So when we take data, we model it. So we take the data and we manage, let's say with the LC922, we model the data, we create a model, and then we pass it on to something which is going to do inference, or if you're a human, you'd call them being judgmental. So when we see something, we form an impression, and that we are inferring things from our experience. So on the IC922, again, a high number of cores at 4 threads. Both sockets must be populated. Maximum memory is 32 slots, and remember 50% gives you 340 gigs a second, whereas if you go to 32, they all run slower, so you get 306 gigs. So maximum performance is 50% populated. So we can pop in this box, we can use the Tesla T4s, and we can fit 6 with a statement of direction for 8. And these all connect via PCIe. So at the moment, we've got PCIe 3 cards. We've got some 4 and some 3 slots. We have statements of directions for field programmable gate arrays, and ASICs to come. So an ASIC is typically a pre-programmed chip that does something very well, be it a RAID controller or something like that. That's all it does. You can't reprogram it as you can with an FPGA. So support for those is coming. I'm not saying they are coming. It's a statement of direction. There are disclaimers normally when we make announcements like this. And I said it's storage rich, so we can have 24 2.5-inch drives up to 3.84 terabytes, and SSDs or 2.4 terabyte hard drives in a 2.5-inch form factor. And we have a statement of direction for an NVMe backplane, so increased throughput capability from the NVMe, statement of direction coming along with the statement of direction for 8 GPUs and statement of direction for field programmable gate arrays, etc. PCIe cards are required for the storage, so you lose 2 slots. So even though, if I remember correctly, I said there were 10 slots in this box, you can start using them quite quickly. Processor interconnects are 2 of them. So we remember some of our earlier systems like the LC had 60 gig. This has got 120 gig connections between the CPUs. And 10 PCI, yes, there we go, 10 PCIe slots, a mix of PCI 4 and PCI 3 on there. And we have 2 of those bricks available for OpenCAPI 3. We don't use NVLink 2 on this box because we're using GPUs that plug into the PCIe slots. And Red Hat 7.6 or later, make sure you get the alt version, which is specifically for the IC922 and power. So here's a quick picture of how the GPUs go in and the order that they go in the system. So we put the horizontal ones in first, number 4. These are the T4 GPUs. This first one, second one, third vertical, fourth vertical. So you can see we're spanning across the 2 sets of buses, 5 and 6. And at the moment, we have no OpenCAPI FPGAs, but they will be being developed and continuing to come forth. So just a wee bit about workloads and some of the workloads that we've done, particularly in ANZ. One of them is photo colorization. And I've got some examples here of colorized photographs. So on the extreme left-hand side, that rather attractive baby is me in 1959. And it was colorized by a supercomputer called a human in those days. I know this because my mother's teeth were never that white. And and you can see how things were missed out. So it's predominantly a black and white image with just a few dashes of color put on it. So the sill here on the property was not gray, but we all know that bricks are red. And we'll put a little bit of color in on the mullions here in the window frames, and just a little bit of tint on the screen and lipstick. And if I were to zoom in, you would see that the hair is predominantly gray with just a wash of color coming through it. So my colleagues in Australia are responsible for the pictures we see on the right-hand side. And what they did is they worked with News Corp. So historically, right back to the 70s and the 80s, right through even the 90s, as we can see here, newspapers didn't print in color. And so the photographers only used black and white film. And if you want to be a news photographer, you want to make sure that you're getting the best capability of taking photographs. So you tended to use what we call a fast film, maybe 200 or 400 ISO. And in those days, the actual grains in the emulsion are larger than a landscape film with 64. So you see that on a digital camera when it says, what do you want your ISO to be? It's pretending to do this. So here we have a picture in 1990 when the AFL was using Tina Turner to promote Simply the Best. And so here is there's ET on there if you follow rugby league. And then this one from 1975 was the government being dissolved. Gentleman's reading a speech, and that's Gough Whitlam, if you remember your history in Australia. So what we did was we worked with News Corp and the photographers, so I've given the credits to the photographers here, to colorize some of these photographs. And there is a whole 2-page spread just recently that you could find, and I'll put a link up to the blog from Adam explaining how we did this. Because what we end up doing is these are obviously taken on film, and so they get what we call noisy. So there's the grains, the individual grains, particularly obvious in the right-hand picture of Gough Whitlam there. You can see the actual grain size. So what we try and do is get rid of that noise. So you get noise from the grains, you get noise from the scanning, and you get noise from the compression to the JPEG. So what we have to do is we have to denoise them. And then these were taken, 1975 and scanned sometime in the last 40 years. And so most of these images were only 3 megapixels in size. And your iPhone today takes 12 megapixel pictures. So what we had to do is try and make them able to be printed in a large format. So we had to scale them up. And then we had to colorize them. So what we end up doing is doing 3 models. So we denoise them. So what we do is we take and we have to scale them. So we take a good picture, a large quality, and we descale it down to a lower resolution, and we make a model on that, and we make a model on colorizations, and we make a model on then we do an upscale, shall I say. We take a big picture and scale it down. So we take a small picture and learn how to scale it back up, which is what I'm saying. We do the option in reverse. So, and this is what we came out with. So this has given IBM and its AI some great awareness, particularly in Australia. I think we'll be seeing some more of it, and it may even come into New Zealand. We may try and do some colorization of historic photographs here as well. But that's one workload, for example, we've used it for locally in New Zealand. And this takes 1 or 2 seconds really now to colorize the things. The more images you've got, I mean, you and I can take our scanners and we can upscale and we can downscale, but it's just that you've got to do that millions of times. So we automate that process. We use an IC922 to do the learning and the training, and then we just pop pictures up and it would go, okay, this is what I recognize. I'm going to train it like this. I'm going to fix it like that. And here's a color. How do you feel? So some of our use cases for AI, Visual Insights, used to be called Power Vision AI. It's a great drag drop user interface. And you can augment. So for example, if we had cookies going down an assembly line, and we have broken or deformed cookies, we can take pictures of those and we can say, this is a bad cookie, this is a bad cookie, this is a good cookie, etc. But then what happens if the cookie is turned around 18 degrees or 30 degrees? It's not the same as it was before. So we can augment that automatically to say, here's some filters we can add and go, we can blur it, we can rotate it, we can flip it. So you might have 9 pictures to start with, for example, and you have 150, 200 pictures very similar by using these filters. So then as more and more cookies come through, the more training happens, etc. We can therefore infer or identify a product on an assembly line that's defective, and it can be removed through automation. So Visual Insights, we can run them on an IC922 for the training, which uses the GPUs. And then, for example, we use them using multi-cameras at the product inspection stage. So when we produce a server, it has to, does it have a serial number sticker? Does it have the power brand sticker? Are all the filler plates in on the back panel for the PCI slots, etc.? And that can take 10 minutes to do that final exam before it goes out the door, and you catch anything that needs to be done through rework. Because if it hits the floor, if it's a car with pieces missing, for example, a badge or a wing mirror or something like that, and it gets to the dealership, it's got to go all the way back to get reworked. It's very, very expensive. So what we did was we have a little station with multiple cameras. We trained the system with the images, what we wanted to identify, where it should be. It does it, and it can do that whole check in 1 minute. So we still need subject matter experts to set these things up. Humans need to train these things. All it does, then it makes it faster. So insurance companies, there's a brilliant little app that the insurance company in Japan, I think it was, did, where they are rapidly responding to damage claims through AI interpretation of images that a claimant would submit. So they take a picture of their little fender bender and their wings dented or so on, and it goes through the system and automatically says, we know what that car is, we know what the damage is, we know what the likely repair cost is, here's an offer. And that could be done in as little as 30 minutes. Whereas the bigger systems, humans have to go through it. Is the chassis twisted? That bigger crashes and things like that. So again, they took thousands of pictures of vehicles, and they what we call segmentize them. We take the bit that's wrong, so the bent panel. It works out what that is. It can tell, is it just the fender, or has it gone onto the wing? Has it gone onto the bonnet? Is the roof rippled? That sort of stuff. So, and by knowing all these items, as I say, it can build a quote and a claim and make a proposal very, very quickly. Another tool we have, which builds on the learning, is a thing called Visual Inspector, and that's an IBM app for Apple iPhones and iPads. And this can do inference, which it takes from an IC922. It can do it either connected or in standalone mode. So when we look at our phones now, we've got AI built into this, not facial recognition, which we're not talking about anymore, but for example, my camera, there's a setting on there, take the photograph automatically if you see a smile. So it's recognizing facial recognition, takes the picture. Mine won't work. I don't smile enough. But in this case, for example, we use this Ford, and I believe we've also used it at Volkswagen, identifying in one example I saw to make sure that all 5 wheel nuts are on and all 5 wheel nut covers are on, that little plastic sleeve that goes over the wheel nut. So that was trained, and the images from good wheels and bad wheels were put in, sent back down to the iPhone, running in standalone mode. And as each car comes along, we could have one on each corner. Each car comes along, it goes, are they all there? Are they all black? Yes, this is good. Or maybe one's hanging off partly and it's not quite sure. So it can actually take the beauty of a camera or an iPhone is it can take a picture, and that can be sent back for more training. So it's an iterative cycle when we do this. So as I say, Visual Inspector for that. Ford did one. They'd spent hundreds of thousands of dollars trying to get an inspection working. And basically one of the IBMers went round and took photographs of cars and trained them and said, these are good, this is missing. And he went back a week later with an app and said, here, try this. And they're rolling it out to, that was in Chicago, they're rolling it out to 30 more plants, I think around the Chicago area as well. So just using a simple training for visual insights and putting the inference capability onto a portable device is absolutely sensational what you can achieve. And the last one I've got on here for a sample of a workload is the SAS Institute. So SAS Institute typically ran on AIX using the 9.4, so they would provide analytics to companies. SAS have actually seen the value of the power server and have decided to make the VIA, which is their new, more visual product, work on Power 9. And so Red Hat only on the solution. And what SAS IT does is more of a grid solution. So it is the opposite of virtualization. So where we make one server look like multiple, what a grid solution does takes multiple servers and makes it look like one. So we use some very smart software from the Spectrum capability that we've got, LSF, and we share workloads around the various servers. And we can now, obviously with more image related, we use the IC922, and VIA is going leaps and bounds with that. In fact, if you're a business partner or an IBMer, have a look on Seismic and have a look at the VIA SAS and Power training that's available to you. So some IDC comments on value share. This was late last year, if I remember. We're paving the way with AI and capturing #1 position in the global market share with AI services and AI software platforms. And look at the values here that AI is going to bring forth. From 28 billion in 2018 to 98 billion in 2023, which is in a few years' time, compound annual growth rate of 28.5%. So we're what we call the tipping point of machine learning and automation, providing developers with the power to advance learning models. So we're into it. COVID slowed things down, I would think. People are trying to work out where they're getting the best value. People will need to understand that they have to have lots of data and they have to have good data. So here we are, IBM #1 in market share, IBM 1 in AI services, and #1 in software platforms. And I'm going to wrap that at 4:55. Thank you very much indeed. Thank you, Ablio, for doing the first bits for us.
I have a very interesting inquiry here to start to discuss a little bit about why it was about storage firstly. So why you don't use mainly object storage for the whole AI platform? It seems like our competitors are using this a lot, and they claim to be having a good success on this. And I didn't answer on the Q&A because I would like to share my view to everyone. So firstly, it all depends on the application. If your application talks S3 natively, yeah, it may be good to have an object storage, but imagine that for more data from different sources, the better, right? So more information we can mix and match and do our mining to extract useful knowledge from it, the better. So depending on where in the AI ladder you are, you need to have more performance and less or more capacity. And you can't control that. It is workload oriented, right? So from that perspective, you need to have flexibility. And imagine that you have a single system that talks just one protocol, S3, for example. You don't have too much choice unless using only S3. The point that we are making here, as we have everything from the data point of view, you can mix and match, fitting that for the best performance when it is needed, like in the inference and the ingest, and in the same within the same infrastructure, data infrastructure, you can have capacity when it is needed as well. So that's why I reckon that it is more complex than it seems, right? And there is a question that Ben already answered to me. And so I hope that I could address the point about ICOs being the only support for this. So nothing against using S3, but it is just matter of if that is enough for your application. If it's not, we need to put another tier, and you need someone to manage that. So that's it. I have a question from Benjamin Kwan, your seller, which I tend to ignore because you guys can talk privately, right? So, but yeah. Okay. So more questions here. How do we determine the number of GPUs required for the application?
Yeah, that's a question. It depends what you're going to be doing as well. If you're going to be doing the training. So one thing I didn't cover was the difference between the GPUs in the AC922 and the IC922. So the AC922 has far greater accuracy, shall we say. So if you were to do an AC922 for training and you decided to do an AC922 for inference, then you really got an overpowered solution for the inference part. If you haven't got the dollars that you might need to invest on an AC922, and obviously IC922 has cheaper PCI-based GPUs, could you do the training on it? And the answer is yes, you can, but it won't do it as fast, shall we say, or to potentially the accuracy that the AC922 would do it at. So the number, I'm sorry, I don't have a straight answer as to how you would decide whether you want 2, 4, or 6. I guess it depends on the workload and the application size and what application you're doing. So our team in Australia who support us have specialists in this area, and if you've got a specific question, I can fire that through to the guys, and say, my customer wants to do this. How many GPUs do you think I need? Quite often it comes down to what you can afford, to be perfectly honest.
Yeah, a lot of it, just
Okay.
to add to that as well. I think Adam has always said that it comes down to the end user experience. Obviously, the more GPUs, the quicker you can get
Yeah.
through. But at the end of the day, it's down to how quickly you want the model to run.
Yep.
Yeah,
What type of data
that's
it
pretty
is?
much it.
Is it visual? Is it visual data, or is it and just analytics and numbers? What are we looking for? Are we looking for trends?
Hmm.
For example, my supercomputer knows that if it's a Thursday and it's raining and it's a long weekend tomorrow, driving is going to be terrible. I mean, I know that, but does a retailer know, or does a tow truck company know to put more trucks on the road and get more staff in to get those crashes cleared away? So that sort of stuff, analytics. I mean, that's a really high level example, but it's that we know it, but computer systems don't, and they have to be trained to do those sorts of things. So if you want something to be working now, you want interactive information, then you've got to put more power at the edge. So where it's nice to have the inference on an iPhone or an iPad, like I was talking about, and it can do stuff, the workload may be too big for that. And so you might need to put an IC922 out at the edge with bigger GPUs and actually doing some more work. So it all depends on the application, what you're trying to achieve. And most importantly, I think I really probably should have said it right at the beginning, is what is the business benefit you're looking to get out of AI?
Yeah,
A lot of people,
true.
we've got to do AI. We've got what's the business benefit? What are you going to do? Because somebody has to pay for this, right? And it's not developed the way a traditional application would be developed. The skill set's different. The cycle of development is completely different. If you think, a development manager will move into, it could be so foreign to him, he might feel really, really frustrated. And as I say, a lot of projects will fail because they haven't got clean or enough data. Can't stress that enough.
That's good. Prasanna was talking about maybe having a session about an example of sizing in a small application, very controlled environment. So we can say maybe we need to gauge our Aussie friends, but the idea of this session, as far as I can understand, is something like, hey, this is the application and this is the infrastructure that we proposed, and that's why it's running fine. So basically that. So if you guys want to see another session on deep dive on this particular topic on how to size it, the infrastructure, just let us know in the comments in the end of the survey. So we're happy to arrange that and send it to you guys. Okay.
Yep. I see Daryl's asked a question there. Do we intend to replace Ubuntu on the Power AI solution? So that's more specific to the AC922. And I think the answer to that will be no on this generation of machine. It it uses the Opal framework. It's very open power oriented, shall we say? And I don't think they'll just redo that with our HEL, but we can check.
Awesome. Guys, any other questions? Let me check if I miss anything. There was a question from Richard, I reckon, about licensing, and Ben already answered that one. There was a question from IH, and I reckon Barry already answered that one. Well, anyway, if you remember any questions that you just didn't send it here, feel free to reach us on the survey. We're happy to fulfill that. Okay. Barry, any comments that I missed from the storage part, which is important to highlight?
I think you covered most of it. Just I answered that question as well in the chat about object. Um, I guess it's probably just my partially my snobbery as well of when it's like comparing iSCSI to Fiber Channel. Do you want a proper protocol or not? So there's uses for it, and obviously, as you say, if everything is in is in an objectified form in the first place. And the nice thing with objects is obviously they've got the metadata already attached to them. But often what you're doing in an AI environment is assigning your own metadata to them. So that's where I think that ties in with your Spectrum Discover talk that you're going to talk about in a couple of weeks' time, and why that's such an important piece for understanding your unstructured data as much as anything.
Yeah, and that's a very good point, because and as Andrew, or just to tidy up the two comments, just like Andrew just said, right? It all depends on how fast you want to run, right? If you want to take your model can take up to 3-4 weeks to run, and if that is okay for you, that's perfectly fine. But if your company urges to have insight from your AI application, the infrastructure needs to be ready for it, right? And Mr. G, any last comments?
I'm very dark here, I'm sorry. In the South Island, it's getting a wee bit dark. Thank you very much for the people that have attended for my 3 sessions. That's the last that I'm scheduled to present in this 8-week pack. Please remember the 23rd if you're in Australia, New Zealand, for the forum on AI. AI is going to be really big in the next year or so. So if you're looking for, as a business partner or an IBMer, to take an advantage to the market, I would strongly urge you to learn the AI, learn about the Cloud Pak for Data that's now available on Power Systems, learn how we can do a hybrid system, hybrid solutions, hybrid storage, hybrid servers, and take that to market and show our differentiations.
Awesome, awesome. Yeah, well, the last comments are the same of every session that we're doing. So don't forget to do your comments. Don't forget to fill the survey that help us to evolve the event as we are doing. Next week we will having Pat Alton on the stage talking about how about replacing x86 by using a mainframe platform for Linux, which was awesome. I totally recommend you to attend it. And that's it. Happy days. We did one more. Take care, everyone, and see you next week. Bye-bye.